Yes, you've seen the title, you heard what I said, and I will repeat myself here again. Vector calculus is a lot easier than you think it is, and I will prove it. I will only need 2 videos in order to help you understand the overall vibe of vector calculus, the so-called, let's just say, important stuff of vector calculus. So let's just talk about what do I mean by that. If you will learn vector calculus in the future, or you have already learned it before, you will know is that vector calculus is huge, very large, and there is a lot of rules and equations into it. But the important stuff of vector calculus, what is considered as the big 3 theorems of vector calculus: Green's theorem, Stokes' theorem, and divergence theorem. None of these 3 theorems requires you to have a deep understanding of most of the equations you see here in this table. Now, universities loves to put all this idea into your syllabus, and they forces you to do a lot of heavy algebraic exercises in order to master them. However, conceptually, all of these ideas are completely irrelevant to our big 3 theorems. I mean, we don't need vector derivatives, and we also don't need limits of vector functions. If you understand basic calculus, you might even be able to derive it yourself. And we also don't need moments of inertia, density of mass, and center of mass. They should only be taught after students finish understanding the basics of vector calculus, because they are technically just applications of vector calculus. We also don't need Riemann's equations for a double integral. They are way too extra for our situation here. And we also don't need curvature because they belongs to a different topic entirely. So now we can finally actually get into vector calculus. So first of all, what is a vector? A vector is just simply another fancy way to describe coordinates. And let's just say a vector of 3 and 2. A vector 3 and 2 is equal to saying as start where you are, walk to the right 3 steps, and walk up another 2 steps. So this is where you are currently are. Now oftentimes, you would see a vector written in a form of a unit vector. So what is a unit vector? Well, take regular numbers for example, 0, 1, 2, 3, stuff like that. And the distance between each of these numbers and the number that is right next to them are equal and exactly the same way. And that is what a unit is. It is the fundamental distance that is made up of each number. So let's just say if you want to reach 5, you need to take a single unit and stack them up 5 times to reach the number 5. So you could imagine is that a unit is just simply the smallest number that is made up of our number system. So why don't we make our units to be smaller? And that would make it more conceptually accurate, right? Well, yes, but they would still work the same way. And for the sake of right now, we're just simply building the basics of vector calculus. I will just simply use the number 1 as our unit for now. So back to the vector. Here on the left, E is just simply means take 1 step to the right, and J is another vector that says take 1 step up. So now there is a concept out there called a parametric vector, and what it is just simply replacing 3 and 2 with a function, and t here represents time. So you could be wondering, why does time have to do with anything of this? Well, st and yt are just simply a function that represent the distance you have walked in that direction. So now, if you allow time to go by as usual, our vector here would become almost like a tracer vector, and each point that the tip of the arrow points to becomes another distance you have walked. So doing so continuously, you can describe any line or any curve that you want with this way. So that is pretty cool. But did you know that there is actually another form of vector out there. A vector doesn't necessarily have to start at the origin of space. It can start at really anywhere at all. And that is extremely relevant in real life. Take, for example, an electric field. In an electric field, every point in space can be an origin of another vector. So, how can we demonstrate this? Well, in classes, you will probably see these equations a lot. These equations are really not that special. If you see here, in each x and y in both of these functions is basically an origin of a vector that sits anywhere in space. So let's just imagine we plug in a random x and y coordinates. And let's just say that each function gives out a value. And the logic here still works exactly the same as in the beginning, walking a small amount of steps to the right and another small amount of steps upwards. But since here it is negative, we will go in the opposite direction. And so where we end up is basically the tip of the arrow of our vector. Understanding this will make it so that it is very easy to understand what is a vector field. A vector field is just simply a combination of a lot of these free floating vectors. So if you plug in every single random x and y coordinates, and out comes a new vector. And if you continue to do this, it will span out the entire space that is around us. That is really all there is to the foundation of vectors that we will need to use to understand vector calculus. So now we can finally start to get into the actual first part of understanding vector calculus, which is the concepts of line integral. Let's just say that I am at a random spot that has a temperature of 33 degrees Celsius, and the end of my journey has a temperature of 10 degrees Celsius, and each steps on this curve also have their own temperature in it. So a line integral in a scalar field is basically the total amount of temperature I have absorbed on my journey. And f here is a function that tells us what is the temperature of each point on our journey. And if you recall before, with the concept of a parametric vector, each point on a curve can be described as a function of x and y with a common variables as t, which is time. Dx here is the actual curve itself, or basically the absolute value of length of that curve. So as you already know, dx is only a small segment of that total curve. So how can we describe dx? Since that x is basically just the parametric vector, the derivative of dx over dt is basically just the derivative of x and y functions over time t. And so if you make dt go to the right, we would have now a general equation for dx. But since that this is a scalar field, the direction of that parametric vector isn't important. So we only need to know the absolute value of length, which is the equation that you probably already learned in school, the Pythagoras equation. So plug into the integral now that we will have a general equation for the line integral in a scalar field. But stop here for a second. The Pythagorean equations used to calculate the actual curve itself, which is sitting in space. But the parametric vector is a vector that is being used to draw the curve. It is not the curve itself. So how can we connect the two ideas? Well, let's just consider the curve that is right in front of us. I'm going to use an idea from calculus is that a curve can be think of as an infinite many collections of points touching one another in space. Here, I am going to zoom in a very specific segment of this curve, and I'm going to have a parametric vector points to a random location, which is, let's just consider the position we are currently standing on right now. And I am going to isolate most of the other points except for the one that we are currently standing on, and the one that is very right next to us that is touching the position that we are currently standing on. At the very next moment, which is time plus an infinitesimal amount of time, which is dt, we would have walked a very small nudge to the right and another small nudge upwards, and where we are currently now is the position that is right next to us to where we were at the very beginning. And if you remember from calculus, is that any 2 points that is touching one another in space can be think of as a straight line. I mean, remember why that this works. If they are touching one another, that means there is no space between them. But since that there is no space between them, no curve can possibly exist. So these 2 points can be thought of as a resultant vector, and here we can use the Pythagorean theorems on them. So that is how the two ideas connect. Now we can move on to a line integral in a vector field. Let's say that this vector field is wind, and they are roughly blowing to the right, and we are walking a motion that is also roughly in that direction. A line integral in a vector field is defined as the work the wind has done on you. Now, work here is a definition from physics, and you probably should go out online and search for other people who most likely can do a better explanation than me. But in hindsight, work is just simply the transferring of energy from something to something else. So in this here is basically wind giving you an extra push to the right so that it is a lot easier to move in the direction of the wind. Now here the equation for the line integral in a vector field looks quite similar to the scalar field version, but in a vector field, directions matters and is no longer about the absolute value of length. So the f functions here and the dx are both a vector, and the multiplication sign you see here in the middle is essentially a dot product operations between two vectors. Here again, there is another person out online that has probably done a better job than me than to explain it. But in simple terms, a dot product is to tell how much does one vector align with another vector. Now alignment here is extremely important. Remember that in physics that we learned in high school, let's say that a box is sitting at that spot and below the x-axis is the ground, is already moving to the right with a velocity v. A vector in that direction pushes the box, it will give the box an extra velocity to the right. However, if the action of pulling and pushing the box, whatever the direction of that vector is, the box realistically should have moved the same direction as that vector. But here in the beginning, since that this vector only resulted in the box gaining an extra velocity to the right, that means the vector that is actually doing the work, making the box going faster to the right, is in the same direction as the x-axis. So, if you remember in the beginning, is that any vector can be think of as a combination of two component vectors, one in the x direction and one in the y direction. And since we know that in the y direction there is ground, so the right direction has no effect on the box at all, and only the x component vector does the work on the box. But now let's go back to the vector field. We only assume is that if we were going in the same direction of the wind, if you are going in the opposite direction of the wind is fighting against you, and if you were going perpendicular to the wind itself actually does no influence on you at all. And we know this to be true because if you allow one ball to fall under the effects of gravity and another ball also under the influence of gravity, but here they also have a push vector to the right. It doesn't matter how much force the right vector is affecting on the second ball. Both of these balls will fall towards the ground at the very same rate, and they will touch the ground at the very same time. So now that we are done with line integral, let's finally go into one of the big three theorems in vector calculus. First of all is Green's theorems. But before we continue, I would like to give you a bit of a motivation why you need to understand Green's theorem. Green's theorems have an application in a device called a planimeter, and a planimeter allows you to calculate the inner area of a very weird shape. And this is very usable in real life. For example, in healthcare, you can use it to calculate an organ or a tumor, which is obviously have a very weird shape. Or in mechanical engineer, you can use it to calculate the area of an engine indicator diagram. Well, that is pretty cool, but at the same time, you feel that it is quite niche for something to be taught so commonly among all engineering disciplines. And that is absolutely true, because there is another application of Green's theorem that I won't reveal for now. And this application is extremely important for all engineering disciplines. Now we can start to understand Green's theorem. First of all, look at this part on the right. The left component asks us how much does the vertical force changes as you move horizontally. Here, I will make it so that they increases. So that means, imagine it's like holding the two ends of the stick. If you pull the right ends stronger than you do with the left one, this stick would basically experience a counterclockwise motion. And here, on the right component, asks us how much does the horizontal force changes as you move vertically. And again, I will assume that it is larger, so this stick will experience a clockwise motion. Also, keep it in the back of your mind is that in this animation, there is some space between these two dots in both the left component and the right component. However, in reality, there should be no space at all, and the two blue dots are actually touching one another. So now we ask, if we take the left component and minus the right component, would it be a counterclockwise motion or a clockwise motion? Here again, I will assume that is that the left component is stronger than the right component. It would have a counterclockwise motion. Now, you probably think that I made some really rather bold assumptions, but bear with me here. It will come back to us beautifully later on. Here, there is an important distinction I want you to know, is that this operation you see here is all happening within an infinitesimal space. What does that mean? It's essentially just four dots touching one another. Again, the animation shows you that there is a small empty space in between, but remember that it is just a visual effect so that you can actually see what is going on in the future. The net counterclockwise will make that this infinitesimal space spin around counterclockwise motion where they are standing. So you might be thinking, how is that even important at all? Well, there is another unit of space to the right. But the key here is that these two units of space share a common middle wall, and the net counterclockwise rotation is the same for both units of space. So the effect from the left unit of space will cause this common middle wall to go up, and the effect of the right unit of space will make the common middle wall to go down. And so there is two opposite reaction force here, and they will cancel each other out. Here I have another animation for you guys to see. So one might ask is that even though that they are in opposite direction, how do we know they are also equal in force? And the answer is that regardless, they are still the very same vector field in both regions, and they are being evaluated at the very same points on the wall. And this logic can be applied at the boundary on the top, or at the left, and at the bottom as well. And so, as you can see, as long as there is a point, they can be used as a boundary for the cancellation process as before. And one final idea to build Green's theorem is that do the same for all other regions, and when you do that and zoom out, the only boundary that is not cancelled is the outermost boundary of this closed curve, and this is essentially the left-hand side of Green's theorem. Now let's go back to the three assumptions that I made along the way. Now some of you guys probably already realized is that you just can't assume that they will be positive, and they are right. But here, just focus on the last equation, the difference in derivatives, because that is the final result that we want to see. And whether this result is positive and negative, it is actually not that important. For example, let's just say that you are standing on planet Earth. If there is a man that is on the other side of the planet, for you, that man is in the negative direction, but for him, you are in his negative direction. So they are all relative to one another. And since that we use the counterclockwise direction as the logic to build Green's theorem, and if the difference in derivative happens to be in the opposite direction of counterclockwise, all we have to do is add a negative sign on it. And that is all there is really to Green's theorem. So now we can ask ourselves, what is so powerful about Green's theorem, such that it can be taught in so many different engineering degrees? Well, that is because Green's theorem is literally just Stokes' theorem. And the only difference is that Stokes' theorem is in 3D. So in a 2D plane, with a closed curve and its inner area, that is Green's theorem. Stokes' theorem is just basically bending that object upwards into a 3D space, just like how bending a piece of paper upwards. And this triangle you see here in Stokes' theorems, well, they are just a shorthand for this. Same exact logic as Green's theorem, no different at all. And what is so special about Stokes' theorem is that they are used to describe Maxwell equations. And Maxwell equations are literally the foundation for all electronics. Stokes' theorems can also be used for stuff like aerodynamics, drones, planes, rockets, you can name it. This video might last a whole day if I do. And this is the end of our first video. And what I want you to have out of this video is that vector calculus, but also every other mathematics subjects that you might have learned in school, not only of their fundamental concepts, but all of their applied methods can be explained using some common intuition and visual effect. Knowing this, I hope that you will be less intimidated by mathematics and learn how beautiful it can be.